Okay, so I'm just going to go ahead and read what we've got here for lesson 10.1. It says, in this lesson, we learn a quick hypothesis test for testing the existence of linear correlation. That's just a linear relationship between two variables, not necessarily cause and effect. As a reminder, the sample linear correlation coefficient is R. We generally use technology to compute R because the formula is unwieldy. Love that word. The population correlation coefficient is rho. So that's a Greek R, and it looks like a P. So we're still kind of thinking of this as correlation coefficient. R is the correlation coefficient, but if it's a population correlation coefficient, we always use Greek letters for population parameters. So we use the Greek R, which is rho. Okay. If rho is 0, it's the same as when R is 0. We have no relationship between variables. So it says if rho is 0, then the population of XY data points exhibit no linear correlation. If rho is not 0, then at least some linear correlation exists in the population of data points. So we're going to have a null hypothesis, an alternative that's always the same here. We're going to claim that rho is 0, okay, with the null hypothesis. So that, again, means that there's no linear correlation. Okay. And against the alternative hypothesis that linear correlation exists, okay, so, and as always, we assume the null hypothesis is true. Okay, so we assume there's no linear correlation. Under this condition, the mean of R values is 0. Okay, so that's just saying the expected value of R is going to be rho. Okay, and rho is 0. So the mean is 0. And the standard error is a formula. I think I proved this in the book, if you care about that kind of stuff. So this turns out to be the standard deviation or the standard error, and that's a difficult argument. The standardized value for this, meaning when we take a z-score, it turns out to be a t-score, not a z-score. Okay, so the standardized value of it is the student's t statistic. So this is your test statistic for the hypothesis test. So normally you would take the R, subtract its mean, and divide by the standard error. Well, I'll just go ahead and put standard error, which would be the standard deviation of R values. Okay, so R is just R. The mean of R values is 0, and the standard error is this thing, square root of 1 minus R squared over n minus 2. Why n minus 2? That's complicated, and I almost don't want to talk about it. So it's R over square root of 1 minus R squared. So this is your statistic for this hypothesis test. It's just a t-test, but the degrees of freedom, again, are n minus 2. Not n minus 1. So complicated. I'm going to read it because I can't imagine saying it better than I've said in the past. Okay, so here I am. This is a two-tailed test with n minus 2 degrees of freedom. Because the standard error uses 1 minus R squared, which is SSE over SST, and the sum of, okay, SSE is the sum of squared errors. It tends to be too small because we're using two sample statistics to compute it, the sample slope and the sample y-intercept. Basically, they're saying that R is measuring distances from the line of best fit. And the line of best fit has a sample slope. I'll go back up to the line of best fit in the previous lesson here. So we had computed the slope from the sample for the line of best fit and the y-intercept for the line of best fit. And those are what gave us the line. And remember, R is a measure of how close the points are to the line. It's sort of a measure of variation from the line. And variation from the line is related to the standard error. The standard error is where we get degrees of freedom. Variation from the line depends on the line itself. Really, we want the variation from the population, the line that, I should say, the population regression line that would use a population slope and a population line intercept. The population line won't be as close to the data as the sample line because the sample creates its own line. And so the line is as close to that sample as it could be. The population line would be farther for two reasons. Okay? It's farther because we're using the sample. The population line is farther because we're using the sample slope. Okay. Pardon me. And the population line is farther because we're using the sample y-intercept. That's two things that make the population line farther away and two things that make the distances from the sample line closer. In the end, the standard error is too small because the line is too close to the data points, and it's too small for two reasons. So we make the standard error bigger, just as we did with the standard deviation, where we divided by n-1 because we were using a sample mean instead of a population mean, and that makes the standard deviation too small. Here, the standard error is too small because we're using two sample statistics instead of two population statistics. And every time you use a sample statistic in one of these sample standard errors, it makes the result smaller than it should be. So it's smaller because of two hits. And so we have to correct it twice by subtracting 1 each time from the denominator. And you end up with an n-2 in the denominator. How's that for a complicated explanation? Okay, so it says we want to conduct the test for the data that we have here using a 0.05 level of significance. So this is just like every other test. I should say that the assumption for the test, or requirement if you like, is that the XY pairs exhibit bivariate normality. All right, so that's a really complicated issue. And
Professor, excuse me, I'm sorry. My screen is still on.
Okay, I hear you.
Okay, thank you.
Yep, I hate it. Okay, it freezes. All right, so this is where I'm at. Now, did you guys get the standard error? Then you did, right? I think you did. So we're on the next page again. So I'm just writing down the requirements for the hypothesis test. Okay, and we will assume that this is true, that the data pairs that we have are from a bivariate normal distribution. Basically, a bivariate normal distribution sort of makes an oval shape when you draw a curve around them. So if you look at the data points, you can kind of envision sort of an oval shape. And you know, maybe I can show you a picture of a bivariate normal distribution. I'm hoping we'll get some nice pictures of these. Here you go. That's a great picture of one. All of these. And so think of that as a two-dimensional bell curve, or I guess it's three-dimensional bell curve. Okay. And so you kind of have to do a three-dimensional bar graph to decide if data points look sort of like a bell in 3 dimensions. And so that's the requirement. And there are ways to determine this, obviously, but it's sort of beyond. And I like this one here. That's a great picture. So what they're saying is that a bivariate normal distribution will be normal. I don't know if you can see this one, but it's showing you normal distributions in X and Y. Where did the picture go? Darn it. Way down here. Okay, it's not there. Oh well. Oh, there, that one. What a beaut. So what I meant, well, there's the oval I was talking about. Bivariate normal distributions, when you graph them in a plane, if you do a scatter plot of all the data points, they should make an oval like that, with where the points are more dense in the middle. Okay, and the density is sort of the height of the bell. So it's more dense in the middle, which means the bell would be higher there. Now, those 2 bell curves they draw there, those are they're saying that it's normal in X, so they have an X bell curve, and it's normal in Y, so they have a Y bell curve. Isn't that complicated? But that's what they're getting at when they say bivariate normality. So I drew a little oval here over these data points, and I admit that's pretty lame. But I'm just trying to explain what I'm talking about there. Okay. All right, so yeah, that's a requirement for this test. And there are some things you can do, but we're not going to have time to go into all the detail. I'll just tell you that's the requirement, and if you really want to look into it, you know enough at this point where you could study this. But right now, I'm just going to tell you to assume that the requirements are met. Okay. So the null hypothesis is exactly as it says above, that the population correlation coefficient is 0. So there's no population correlation between X and Y. Okay. And then the alternative hypothesis is, well, you're just saying, okay, that's not true. So rho is not 0. Okay, so that would just be to say linear correlation exists. Okay. I'm not saying how much. It could be weak, but I'm just saying there is at least some linear correlation with that statement. Okay, we have a test statistic. That's above. As I say, it's a t-test, so there's your t statistic. So I think I'll just copy that down. Okay, and I think we have an R value, so let me grab the R values from the previous page right there. So here's R, 8982. And N was 8. Okay, so that's a little bit of an ugly computation. And again, it's best if you try and just pile all that into one computation on your calculator. So I'm going to just show that in case you care. Okay, so a fraction, 0.8982 on top, square root, on bottom with a fraction, 1 minus 0.8982 squared over n minus 2, so it's 8 minus 2, which is 6, of course. Okay, so you just want to try and get all that in. One computation. Why? Man, every time you round these numbers, the answer just gets worse and worse. So this, doing it in one shot means I'm not going to round anything until it's done. Okay. So there's your t statistic. That looks pretty big. 5.00. Maybe just to make sure it's not, we don't say 5, let's say 5.005. Okay, any questions? Okay, remember the degrees of freedom are going to be 6 here. Okay. That's a really high t statistic, and I really don't know that my table A3 goes up that high, but we'll take a peek. So table A3 for t p-values. Has the degree of freedom going across the top. So that's going to be 6 degrees of freedom. And then our t statistic goes down, and you just have to look up 5.0. Like that. And you could use a p-value calculator that I posted in Canvas as well, which is always more, it's going to be more precise, right? Tables are sort of like, oh, well, this is the best we can do. And the computerized p-values are much better in general. We're ready. So let me bring up the table A3 real quick, if I can find it. Okay, I'm going to have to work a little harder. Bit of a mess. Okay. Now the 5.0 is way down there, but a 6 degrees of freedom. I got a 5.0 in the last table. How convenient. All right, point. That's actually surprising. So we'll use 0.9988. Any questions? So there's how you use, if you're like, well, how do I use table A3 to get a p-value? I mean, this is, but you have to remember this gives the area to the left, which is not what I want right now. I'll draw a picture. Again, it's 0.9988. Let's go back to our notes. It's a little bell curve. It's a T curve, not a Z curve. Okay, so we looked at 5.0 here. I'll put 5.005 just because. And then the area of, oh, sorry, my bad. Oh, that went all the way to the top. Okay. Okay, so 0.9988. Remember, these tables always give areas to the left. So the tail is like 0.00. What do you guys think? I think it's 0012. Is that the p-value? Thanks, Susan. Is that your p-value? Ladies and gents, yay or nay? It's not. I tricked you. Why is it not? Look at the alternative hypothesis. Look at the alternative hypothesis. Why is it not?
You have to multiply by 2?
Yeah, this is a two-tailed test. So you got to double this one. Remember, not equal on H1 says two-tailed test. okay? The tools we use have no idea of that. You have to do this yourself. So it's 2 times 0.0012. So that's going to be 0.0024. You guys all right? 0024. That's still really small. So I don't remember what alpha was, 0.05. So our alpha, well, let me do that. P-val is 0.0024 less than 0.05, which is alpha. And when it's less, you know you'll reject the null hypothesis and support H1. H1 is the one that said that linear correlation exists. And I'm not going to say linear correlation exists, but I am going to say that the data support the claim that linear correlation exists. Way under the margin here, the data support the claim that linear correlation exists. And I'm going to get real cryptic here. I'm going to say between auto weapons. See, I don't have room. What in the world am I supposed to do? Between auto weapons and murder rate. There is a correlation. Strong? Yeah, I mean, we said it was strong on the previous page because R was bigger than 0.8. Okay, and not only is it strong in the sample, but it's strong enough in the sample to say that there's a correlation in the population of all cities. So now, again, when we do hypothesis tests, you're generalizing beyond your sample. We have enough evidence. Most people always talk about the data. Do you have evidence? Yeah, we've got evidence, and it's strong. Okay? There is a correlation. Is that an argument to ban automatic weapons? Only if it was causal, and it's not. Okay, and believe me, I'm not a fan of guns. I'm just saying it's not. It's not simple. Okay. And acting like it's simple, just sort of ignores reality. How you doing out there? Out in cyberspace. I don't even know if you guys are real people anymore. I have like this hypothesis, this null hypothesis, that all these rectangles I look at are just rectangles. It's crazy. I don't know. But I do it every week, and the money keeps coming in my paycheck, so I gotta keep doing it. I'm not gonna stop. Sheesh. All right, any other questions? Yeah, see? You're not even trying to prove that you exist. All right, fine. Now this bit here, so that's it. That will be on the final. Any questions about it? Last chance. Okay, for sure. Now there's another super interesting thing here that I don't think I can put on the final. Interesting to me, because I'm a math nerd. This is a test for normality. We always talk about how, yeah, evidence for normality, because t-tests, when we have sample sizes that are small, less than 30, you may remember. If you don't have a large sample size, you have to provide evidence of normality. And in the past, we've always just drawn a histogram. And if the histogram kind of had high, middle, and low ends, we said, yeah, that we would say, yes, that's evidence for normality. But it's sort of subjective. It's a matter of opinion. And in statistics, we don't use opinions. We use data and evidence, so and not subjective evidence or data. So this test allows us to sort of be able to say, yes, there's evidence for normality on an objective basis. So let me go ahead and read this. So it says, in this lesson, we introduce a hypothesis test that investigates the normality of a population using sample data. Here are heights of 9 men randomly selected. We want to know if they are sampled from a normal population. Okay, so let me just double check. I think these are sorted from low to high. They are, and that's important. So I'm going to make a note of this. And you'll see why it's important. Okay, so I don't know if those are from a normal population, but what I'm going to do is I'm going to compare them to numbers that are from a normal population. So let's keep going. It says, but what does a normal collection of data points, how about, look like? Okay, technically speaking, a perfectly normal sample of 9 values would be separated by areas of equal probability on the normal distribution. Huh. Below is a standard normal Z distribution. There are 9 lines separating 9 Z-scores that are separated by equal areas. It says find the areas and then determine the Z-scores. Yikes. All right, this sounds like a pain in the butt, but let's go with it. We could probably be really precise about this. Let's see, there's 9 values. How many areas are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 areas. Oh, okay. So if you have 9 values, they have to be bounded or separated by 10 regions. Okay, I guess another way of saying that is that 9 dividers can divide the number line into 10 regions, which is what we've just seen. And if you take the total area, which is 1, and divide it by 10, what are all the areas? Go ahead and type it in, somebody. Oh, by the way, I just want to let you guys know that when I'm trying to be funny and you don't think it's funny, just remember who gives out the grades, okay? So you could like pretend it's funny. That's a joke too. No, I'm not. Yeah, thanks, Susan. I'm totally, yeah, good job, Alexander, way to go. Way to go, Jason. You guys all get extra credit today. Thank you. 0.10 is the area of each of these little slices. Okay. This is how normally distributed values should be arranged. Okay, I don't know the values yet, but they should all be separated by 10% regions if there are 9 values. Okay, so that's the first thing. Now, what's this first Z-score? Well, I know the area to the left of it is 0.10. Okay, and when we knew areas on the normal distribution, we found Z-scores with table A1. So let me show you this real quick. I'm gonna have to leave here and go into that table real quick. So table A1 is this guy. And if you're looking for, by the way, I don't know if you noticed from the picture, that's gonna be, remember 0 is in the middle of the Z distribution. So this is gonna be a negative Z-score with the area to the left of 0.10, okay? So just real quick, I'm looking for an area of 0.10 on here. I'm getting close, and I don't know if you're seeing what I'm seeing, but I found a 0.1003, and that ain't bad, okay? Look at that. Negative 1.28. That is the first of my Z-scores. Okay, you guys follow that argument? negative 1.28. So let's put that into the notes. It looks, you can see it's kind of fits with the picture here, negative 1.28. That's my first z-score. I'll put it down there. Okay, the next z-score has an area to the left of 0.20 now. Let's get it. Oops, wrong table, hang on. Okay, so the next one's 0.20. Find it? See, there's a 2005 here. So that goes with a negative 0.84, I think. Okay, 0.2005 with a negative 0.84. Okay. Okay, I'm not going to be able to squeeze all that in. I'm going to have to zoom in and do a better job with my graph thing. I'll do that next. Okay, the next one has an area of 0.3 to the left of it, 0.30. So again, let's look for an area of 0.30. There's a 3015, which is pretty darn close. So there, I think you get a negative 0.52 on that one. Okay, oops. A negative 0.52. Okay, and I'm gonna zoom in on my graph and try and do a better job here because I want to be able to post these notes. Okay, so the first one was negative 1.28, except I put that in the wrong spot. Okay, the next one was 8.4. Then a negative 0.52. Okay, I think there's only one left to do because the rest of them will be mirror images. Okay, so we're doing the next one here. The area to the left of the next one is 0.4. Okay, so back to the table. Look for something close to 0.40. Okay, so I see a 4013. You guys see that? So that's pretty close. And the z-score is, you say negative 0.25, you guys? Sorry, that's a little messy this time. Negative 0.25 with a 0.4013. Close enough. So again, this is far from perfect, but it gives me a sense of roughly, and this is going to be good to the nearest 100th anyway. Okay, so the last one's 0.25, negative. And the rest, remember the symmetry of this distribution. So anything on the left is going to be mirrored on the right. So we're going to have a 0.25 and a 0.52 and a 0.84 and a 1.28 here. Okay, and that's what we would consider a perfect sample of z-scores. its distribution is as normal as you can get, as long as you know, you only care about the nearest hundredth, 2 places after the decimal. Let me put these in now. Okay, so negative 0.52, negative 0.25, hang on. And then 0. And then 0.25, 0.52, 0.84, and 1.28. Okay, just like that. And I can see my screen is not refreshing, so let me tweak that. Zoom is disappointing me again. Okay, it looks like I dropped a connection altogether, which is the first time that's ever happened. Hey, there we go. All right, so I've got all the z-scores in here. Go ahead and put them in, but we also want to compare those to Min's heights. So the idea is we're comparing the z distribution to your distribution of data points, and we want to see how well they line up, literally. Okay, so let's go ahead and put in the Min's heights. So they are 63.2, 64.5. 66.6, 67.1, 69.6, 69.7, 71.5, 71.9, and 73.1. Now, I think what I want to do, I want to show you something I was working on with another class I had before. So I'm going to pop over real quick to a distribution where R was 1. So give me just 1 sec while I leave that. And show you something here. Here's a graph right here where R was 1. Okay, it was a positive relationship. The points are going uphill, and the relationship was perfect. So R is exactly 1 on one of those. What I want you to see is that when the points line up on a straight line, that the distribution of the data points has to be the same. So what I'm trying to do here is show you the y-coordinates. It's a little tricky because I kind of have to turn it sideways to help you see, but here are my y-coordinates. Okay, and I'm going to do the x-coordinates in red. Oh, that's not red. I probably should erase all these letters, or these words that have gone on here. So let me clear this up a little bit. Okay, and all I want you to see is that if I copy these data points over here, and then what I'm going to do is I'm just going to grab them and drag them down and help you see that the width is different, but the nature of their distribution is identical. So I'm grabbing those green circles that I drew, turning them sideways, and I want to show you how they line up. Why are there 4 there? I think I did something wrong. Oh, I got it upside down. I got confused, that's why. Okay, so look at how the data points have exactly the same pattern for the y's as they did for the x's. And it looks like I'm missing one. Why is that? I must have missed, I failed to draw one of them. Okay, so you can see this point up here, I failed to draw, and so it would have been mirrored down there. The point is that when two data distributions are the same, then they have a scatter plot that has a perfectly straight line. And so if you think about how that applies to what we're doing now, I have 2 data distributions. One of them is normal. Okay, the other one is questionable. All right. So what's its distribution? Well, what we know is that if we do a scatter plot of these points and they line up on a straight line, then the distribution will be normal. Okay. I don't expect them to lie exactly on a straight line, but it might be close. So let's see what happens. Okay, so the first one, z is negative 1.28 and x, oops, 1.28 and x is 63.2, which is going to be right about, how far apart it is? 64, 62.2, okay, right about here maybe. Okay, the next one is negative 0.84 and 64.5 maybe here. Now the next one's negative 0.52 and 66.6. So this is 66, 5, 60 right there. A little curvature there. Next one, negative 0.25 and 67.1. Maybe there. It's not a perfect straight line, you see. 0 gets a 69.6, maybe like that. Okay, 0.25 gets a 69.7. 0.52 gets a 71.5, maybe right there. 0.84 gets a 71.9. And finally, 1.28 gets a 73.1 like that. Okay, so yeah, that's not a straight line, but it's close. Any ideas how we could objectively measure how straight that is? How could we measure the straightness of this? We have a tool for measuring the straightness of lines, right? That's R. So again, if you go back to the previous page, we had this thing, right? When R is close to 1, oops, didn't mean to do that. When R is close to 1, these points are close to a straight line. And when R is exactly 1, then the points are exactly on a straight line. Okay. So why wouldn't we use, again, we don't want to rely merely on visual observations, which are important, but we also want objective observations, okay? So let me go ahead and read what we've got here. I'm gonna stop in just a couple minutes. It says, if the two variables have the same distribution, the points will line up on a straight line. We shouldn't expect it to be perfect. Do the heights appear to be sampled from a normal population? I mean, I would say that this is close to a straight line. giving evidence of normality. Okay, so to the next page. What tool could we use to measure the straightness? R, which is the linear correlation coefficient. Okay, and then it says compute it below. Okay, let's just do this by plugging in our values. Okay, so just as a reminder, everybody, you do a memory clear, so on plus clear, press data, okay, put the Z's in list 1 and the X's, oops, that's an N, X's in list 2. Let's do it as quickly as we can. Okay, so now, once you get them all in, you press clear. Then second data, and then just pick 2 variable. Oops, 2 variable. And then just hit enter and just hit enter till you get to the statistics, and then just scroll till you find R. Okay, anybody, can you tell me what you get for R? If you've got it, if and when you get it. Again, so once your X's and your Z's and your X's are in, it doesn't matter which order you put them in. Then you press clear, second data, 2 variable. And you just keep pressing enter and scroll till you get R. Yep, 0.9846 is also what I got, which is really close to 1. So that's a strong correlation between these points. Makes me feel like they have a similar distribution. Null hypothesis here for the test says that the sample is drawn from a normal population. The alternative just says it's not drawn from a normal population. We're going to test the claim at a 0.05 alpha that the men's heights are drawn from a normal population, and then try it again using software. We won't do that, but all you have to do is get your test statistic from, sorry, the test statistic is just R. So R was 0.9846. There's no probability distribution, but there's a table of critical values. So the critical R values are table A6. So I'll flip down to the table, just see the next page. Okay, so here we got a 0.05 alpha. This is called Ryan-Joyner test. Our N was 9. Our alpha was 0.05. And the R that's required is 0.912. So any R value less than that would reject the null hypothesis. Okay? There's no degree of freedom. There's not even a probability distribution associated with this. This table is built based on simulations of lots of samples from normal populations. Okay, this is a table based on simulations. It's crazy, but it's called a non-parametric test, which means there's no probability distribution for it. Okay, so 0.912 is the required value. So let me go ahead and put this down. Critical value was 0.912. And the rule is reject HO when R is less than the critical value. That's easy, right? So here, R is greater than the critical value. Okay, which means we fail to reject the null hypothesis, which says that the data are from a normal population. That does not prove it. It's just that we failed to disprove it. Okay. Okay. So generally, when we summarize this, we will just say something like, it is plausible. Not true. Plausible means we may assume it. Okay. So it is plausible that this sample comes from a normal population. What does that mean? It's plausible. You can assume it, okay. And if you can assume it, then you can run your hypothesis test that requires normality. Okay, remember all those t-tests with small sample sizes require normality.